Alrighty, how are you guys doing tonight? Cool. So tonight, it's pretty cool. We're going to start talking about amplifiers. We're going to talk about common emitter amplifiers. This is a particular type of amplifier circuit that you can make with BJTs. So we'll talk a little bit about how those work. We're going to start off with a review like usual. So we're going to talk a little bit about transistor driver circuits. Those are the circuits that we constructed last time, which can either be completely on or completely off. So the transistors act kind of like electronically controlled switches. We're going to also talk a little bit about transistors in the analog range. We did that at the end of the lab, and we created a graph. It was called a DC load line, and it showed how the transistor behaved under various input current conditions. So we're going to talk about the cutoff situation where no current was flowing through the transistor. We're going to talk about saturation, where the transistor acted almost like a wire. And we're going to talk about the Q point. And then we're going to go on to the lecture. So like I said, we're going to discuss common emitter amplifiers tonight. We're going to start off briefly talking about the various classes of amplifiers. So we're going to talk about class A, B, and C amplifiers. I'm just going to briefly discuss what those mean, and then we're actually going to spend the next tonight and the subsequent 3 lectures on these amplifiers. So tonight we're going to talk about class A amplifiers. We're going to touch on class A amplifiers again next time, and then we'll do B and C amplifiers in the 2 lectures after that. We're going to talk about a couple of class A types today. We're going to talk about the difference between a common emitter and a common collector, and we're going to go into detail about the common emitter. Okay. Next time, we're going to talk about the common collector class A amplifier. Okay? So that's the general idea. Any questions before we get going? Cool. Okay. So last time, we started off by talking about transistor driver circuits. And these were the circuits where the transistors acted like an on-off switch. Okay? So the way that they worked was we had something that we wanted to power, such as an LED, and we had a resistor that would limit the amount of current that was going to that LED. So when we were designing these circuits, we would start off just by looking at this part of the circuit. And we would figure out how much current we wanted to go through our LED. Say we wanted 20 milliamps. That's pretty standard for small LEDs. And then we would look at our source voltage. So maybe we had like 5 volts. And then we would pick how much resistance we would need in order to have 20 milliamps flowing through this LED with a 5-volt source. So we could do the calculation. We know that there's 1.5 volts across the LED when it's running. And we have a 5-volt there, so we know that there's 3.5 volts across the resistor. So then you could figure out how much resistance you need to get 20 milliamps with 3.5 volts. So we pick that resistor first. And then what we do is we say, okay, we're going to add this switch at the bottom. And this switch is really going to be a transistor. So we're going to have the transistor there. We're going to have a resistor. And then we'll have this end of the resistor connected to some type of control. Either we could connect it to the 5-volt supply when we wanted to, or we could have it connected to a square wave or some type of sensor, but it would be some control mechanism there. Okay? And then what we did is we figured out how much current we would need going into our base in order to achieve the 20 milliamps that we wanted through our LED. And we did this by using that formula, that gain formula. Remember, we said that the gain of the transistor was somewhere around 100 to 200, right? Usually. So we'll call it 100 for ease of the math. So if we know that the gain is about 100, we also know that that's equal to the base current, the collector current divided by the base current. We can call that IC, collector current, over IB, the base current. So the collector current is going to be 100 times bigger than the base current. So if we know what the collector current is, we can figure out what the base current should be. And we said that that would be the current that we would need under ideal circumstances. If we knew exactly what the gain was, and the gain never changed, and we knew exactly that we needed exactly 20 milliamps, and that never changed, and everything like that. But we said that we live in the real world, right? We don't live in an ideal circumstance. So sometimes this gain does change. Sometimes it's not quite that high. And it can even fluctuate for a given single transistor. The temperature of the transistor affects the gain. So it might be a little bit bigger when you start off, and then when it heats up a little bit, it might go down. So we don't live in an ideal world. So what we do is we give ourselves a little bit of flexibility, a little bit of breathing room. So once we calculate what the ideal current should be here, then we just double it to give ourselves some extra flexibility. So then we know what our base current is going to be, and then we can figure out what resistor we need here. So that's how we were able to design a transistor driver circuit, a circuit that acts like an electronic switch. Any questions about that? Okay, cool. So after we looked at the transistor driver circuits that acted in sort of a binary fashion, either on or off, we spent a little bit of time looking at transistor circuits that operated in an analog range. So kind of shades of gray, somewhere in between on, not really entirely on, not entirely off, somewhere in between. And what we did is we drew a graph. And we called this the DC load line. So this, on the vertical axis, we had the current through the collector, and on the horizontal axis, we had the voltage between the collector and the emitter. Okay? And what we said is that when there was no voltage between the collector and the emitter, the current was at the maximum. And when there was as much voltage as possible between the collector and the emitter, then no current was flowing. Right? The transistor essentially acted like an open circuit. And if you were to plot a whole bunch of points in between these two extremes, you would see that the load line goes something like this. So it goes from the maximum current and it makes a straight line down to the point where you have maximum voltage. And if you look at the spot right in the middle of all this, this is called the Q point.
Can you clarify, are you looking at the middle of the voltage, or are you looking at the middle of the average, or theoretically they're both going to fall at the same point?
Yeah, they should fall at the same point. So this Q point should be the middle of the voltage and the middle of the current. So say we had 100 milliamps at max here, and we had, say, 20 volts there, then this Q point should be at 10 volts and 50 milliamps.
So is that reality, or?
It should be pretty close, yeah.
Okay.
Yeah. Yeah, it should be darn close. So we call it a Q point. Q stands for quiescent. This is, we'll see a little bit more about that today, but basically this is what the circuit is doing when there's no extra input signal. Okay, so if we're talking about an amplifier, this is what would be happening in the circuit when no signal was being amplified. Okay, so you tune the circuit, and you can actually set this Q point when you are building various types of amplifiers. And so for Class A amplifiers, the Q point is right in the middle. We'll see that for some other types of amplifiers, the Q point can be in other places. But for Class A amplifiers, the Q point is right in the middle. Okay? So, any questions about that? All right. Cool. So then, let's go on to the lecture. Let's talk a little bit more about amplifiers. So I want to give you a brief introduction to the various classes of amplifiers, and then talk a little bit about Class A amplifiers before we get into the common emitter. Okay? We're going to focus most of our time today on the common emitter amplifiers, but I just want to show you where they fit in to the bigger hierarchy so that you kind of have that as a background. Okay? So there are three general classes of amplifiers that we're going to be talking about. Class A, Class B, and Class C. Class A amplifiers they have very, very good fidelity. So I guess I could say good reproduction of the signal. So low noise. But they are the least efficient type. Class B amplifiers are more efficient than Class A, but they can introduce distortion. And then Class C amplifiers are the most efficient, but they only work for one frequency. So why do you think you would ever use an amplifier that only worked at one particular frequency? Any ideas? Yeah.
Radio has an intermediate stage called intermediate frequency, and that's always the same frequency.
Yeah.
Calculate it out.
Yeah, that's exactly right. So Class C amplifiers are often used in radio applications. They amplify only a very, very narrow band of frequencies. So for general applications, that's really bad, right? If we're talking, our voice uses a really wide range of frequencies. So you want to amplify all of those equally. Otherwise, your voice would sound weird. But for radio, you actually want to amplify only a very narrow section, because lots of different radio stations transmit on the airwaves, and they're all pretty close to each other. So if you amplified a wide range of those frequencies, you could be listening to 3 or 4 or 5 stations all at the same time. And that would be really hard to do, right? That would sound awful. So for radio, these can be really good for the first parts. And then at the end, you can use one of these other types of amplifiers. So these are the general classes of amplifiers that we're going to be looking at in this course. There are other classes of amplifiers as well, but they start to go into digital signals, and we're not going to be looking at those here. So we're going to be looking at these 3 classes over the next 4 sessions, including today. So today, though, we're going to look at one type of Class A amplifier. It turns out that Class A amplifiers actually branch out into 2 varieties. So today we're going to look at the common emitter, next time we're going to look at the common collector. Okay. So the common emitter amplifier is a voltage amplifier. So this is what a lot of people think of when they think of an amplifier. You know, you put in 5 volts, you get out 10 volts, something like that. The common collector, you put in 5 volts, you get out 5 volts. But the difference is that you get out more current. So the common collector amplifier is a current amplifier. So voltage amplifiers and current amplifiers are often used together, especially in audio applications. So you might start with, say you're thinking about taking music from your phone and playing it out over some loudspeakers, right? The signal that comes out of your phone has a pretty low voltage range, right? It might be, less than a volt peak to peak. So you want to drive these really big speakers. So you might put it into a voltage amplifier first and bump it up to maybe 5 or 10 volts peak to peak, for instance. But this voltage amplifier actually has very, very small amounts of current. So even though it's a 10 volt signal, if you tried to drive a speaker with it, that speaker would just eat it up, and it would not really be able to have any power behind it. So what you need after a voltage amplifier is a current amplifier. So you take that 10 volt signal and you use it to drive this current amplifier, and then that current amplifier gets fed into your speaker, and it can really supply the current that you need to get some big sound out of that speaker. So voltage amplifiers and current amplifiers are often used in conjunction with each other. They're often called stages. So this would be like a preamplification stage, and then this would be the stage that goes right before your speakers. So the common emitter and the common collector are both types of Class A amplifiers. Today we're going to look at the common emitter amplifier, and next time we'll look at the common collector. Okay? All right. So enough of this hand-waving stuff. Let's actually talk about some circuits here. Okay, so you're going to actually get to build some of these in the lab, so this is pretty cool. So let's look at the general circuit for a common emitter amplifier. So this is going to take me a minute to draw, so please bear with me here. Okay. So first of all, you might ask why we call it a common emitter amplifier. Well, what happens is that our output is here, and that's connected to the collector. The emitter is going to ground. Ground is also known as common, so it's a common emitter amplifier. Okay. So what happens is that these two resistors on the left are usually the same value. So they might both be 10 kilo ohm resistors, something like that. You might have a capacitor there. So what this does is this creates a small amount of current that's going into the base. And this small amount of current going into the base allows a larger amount of current to flow from the source voltage through the collector down to the emitter and down to ground there. So say that our source voltage was 10 volts. You would set this up so that at rest, when there's no input signal here, the voltage at the collector would be 5 volts. So that would be the output. So that's our Q point, okay? We would set the quiescent voltage, the voltage when no input signal is happening, to 5 volts. The reason that we do that is because basically when we put a small signal into our input here, we want to get a large signal coming out from the output. And so we want this collector to have the largest possible voltage swing. So if it's right in the middle when there's no signal, then it can go all the way up to the maximum and the minimum when you put a signal in. So if we chose this to be, maybe 9 volts and we had a 10 volt source, then it would only be able to go up 1 volt, right? And then it would hit the ceiling. So we choose it to be right in the middle so that it can go as high and low as possible without hitting either end of our supply voltage. Okay. All right. So let's take a look at this circuit a little bit more closely. Let's say we have a small signal coming in here, all right? So say we have a small positive voltage on the input, right? So now we have a little bit more current flowing from our base to our emitter. So let's draw this out. So say we have a small input signal that looks like this. We want to figure out what our output signal is going to look like. So when we have a small positive input signal here, that allows more current to flow into the base. And if more current is flowing into the base, that's going to mean that more current can flow through this transistor. Okay? So essentially, this transistor is acting sort of like a variable resistor in this case. So when we put more current in, it has less resistance. Okay? More current is flowing through the collector. So if more current is flowing through the collector, then more current is flowing through this resistor as well. And if more current is flowing through this resistor, then you have more voltage drop across this resistor, right? And if we have more voltage drop across this resistor, that means that our output is going to go down. So when our input signal goes up, the output signal goes down. Okay? So our output is going to look more like this. So every time the input goes up, the output goes down. And we can use the same logic to show that when the input goes down, the output goes up, right? When the input is lower, we have less current here, less current there, so less voltage there, the output goes up. So we say that for common emitter amplifiers, the output is out of phase. If they went up and down together, they would be in phase. Since they do the opposite of each other, they're out of phase. So we figured that out. And then what happens is that we want to look at these two resistors. So we'll call this one RC up here, and this one down here RE. Because RC is right before the collector, RC is connected to the emitter. So we have RC and RE there. And the gain for the amplifier is approximately RC divided by RE. So if RC was 10 kiloohms and RE was 1 kiloohm, then we'd have a gain of 10. That means that the output signal would be 10 times bigger than the input signal. So you can choose RC and RE in order to get the gain that you want. But there is a caveat. If you start to make RE too small, then your gain is not very stable. Basically, the transistor can heat up a little bit, and because of some internal physics that goes on, basically the transistor has its own small resistance inside of itself, and as the transistor heats up, that resistance changes a little bit. So if you've got a big resistor on the emitter, then that small resistance change doesn't make much difference. But if you've got a really small resistor for the emitter, then it can start to be about the same size as the internal resistance. And so that small change in the internal resistance can mean a change in the whole gain of the transistor. Yeah.
And it's RC divided by RE?
Yes, I'm sorry. Yes, thank you. RE. Yes, thank you. So you don't want to make RE too small. But of course, you would like it to be small in order to get a big gain out of your circuit there. So there has to be some trade-off. So what you can do is we can add in another component. We can add in a capacitor right here. And this is called a swamping capacitor. Okay? That's this thing. So you might ask, well, why would we do that? Well, what happens is that when you're talking about AC signals, capacitors can act like resistors. Okay? So for AC signals, capacitors actually behave kind of like resistors. They allow some of the AC signals to pass through. They block DC signals, but they allow AC signals to pass through. So if you are trying to amplify an AC signal here, like a voice signal or like a radio signal, then you can put in this swamping capacitor. And the swamping capacitor is in parallel with this other resistor. So what happens to the total resistance when you have two resistors in parallel? Right. The voltage is the same. When you have two resistors in series, you end up with more resistance than either one of those resistors, right? When you have two resistors in parallel, you end up with less resistance. So by putting this swamping capacitor in parallel with this other resistor, you're actually decreasing the resistance for the AC signal. The swamping capacitor blocks out any DC signal, so you don't have to worry about that, but it does allow AC signals to pass through, and you can choose the value of the capacitor so that it can either be easier or harder for those AC signals to pass through. So basically, this decreases your RE for AC signals, and so it can increase your gain for AC signals. So that can be good if you're trying to amplify AC signals. Okay. Just to clarify, this is the load over here. So generally that would be another amplifier, like another a current amplifier. Okay. So that is the basics of common emitter amplifiers. Do you guys have questions about that? Okay, cool. So let's talk about the lab then for tonight. So the lab, you've actually got three parts of the lab, and if you look at all of the parts of the lab, you might start to freak out because it looks like a lot of circuits, right? But turns out you don't have to worry too much. It's just building one circuit kind of in steps, okay? So you do the first part, and then you make some measurements, and then you just add on to it for the second part, and then you do some measurements and you add on to it for the third part. So you're just doing one big circuit step by step. So don't deconstruct your work after the first step, okay? Or after the second one. Just keep it and add on to it, all right? So for the first part of the lab, you're going to be building this left half of the circuit. Okay, so you're going to be building this part, including the two resistor. Oh, okay. Let me start over here. I'll draw it out the way that you guys are going to build it. So you're going to start off in the circuit like this. So this resistor on the left is a potentiometer. So this is going to be used to set the quiescence point, all right? And you're going to connect a meter over here, and you're going to measure the voltage between the collector and the emitter. So you're gonna set the circuit up, and then you're gonna tune the potentiometer here until you see 7.5 volts in your meter, right? Because that's going to be half of the maximum voltage, right? So this first part is constructing the transistor and the voltage divider so that you can set the quiescent point, the Q point there. Okay? So you're going to build that and get that all set up. You'll notice that this resistor down here is also a potentiometer. All right? For this first part of the circuit, you're only going to use the two ends, and you're going to leave the middle loose, not connected to anything. Later on, we'll connect this over to the swamping capacitor, but that's not until later, all right? But you need to put the potentiometer in there now so that it's there when you need it, all right? So that's the first part. You're going to set the bias, and then you're going to measure what the quiescent voltage is, and then you're going to, well, okay, so you're going to start off by finding the saturation point when the transistor is completely on, and then you're going to find the cutoff point when the transistor is completely off, and then you're going to find the quiescent point right in the middle, and you're going to plot all of that information on a graph. Okay? For the second part of this circuit, you're going to add on to what you've done in the first point. So once you set the quiescent point for this potentiometer, you won't touch that for the rest of the lab. All right, you're going to leave that because that's got your amplifier set up. So after this, you're going to take the meter away, and you're going to add on to this circuit. So you're going to add on to the output. You're going to have a capacitor there. And a resistor there. And then you're going to have your input here. And your input is going to be connected to a 1 kilohertz sine wave. Okay? And you're going to use your oscilloscope to measure the input signal and the output signal here. Okay, so this is the whole circuit except for the swamping capacitor, right? So this is going to have a 3 kilo ohm resistor up there and a 1 kilo ohm resistor down there. So what would you expect the gain to be approximately? Yeah, about 3, right? The gain is the RC over RE, so that's 3 over 1. So it should be about 3. So you're going to look at the input on the oscilloscope and look at the output on the oscilloscope and draw both of those on the graph in your lab book. So are they going to be in phase or out of phase? Out of phase. If they're in phase, then something is wrong. All right. So they should be out of phase. And remember, you're not touching this 10 kilo ohm potentiometer, right? You set that up in step 1 so that the quiescent point is where you want it to be. So you're going to leave that alone for step 2. Right. And then for the third part of the lab, you're just going to add a swamping capacitor down here. So should that make the gain higher or lower? Well, it's in parallel with this other resistor, so it's actually going to decrease the resistance. So the gain is going to end up higher. Yeah. And then what you're going to do is you're actually going to change this potentiometer around. You're going to use the dial on this potentiometer to change the place where this capacitor is connected. So basically, changing this around is going to put this in parallel with more or less of the resistor. So it will either so it'll change the resistance down here, and that will change the gain of the circuit again. So you're going to do that while you look at the signal, and if you turn the gain up too high, the output signal will get clipped. Okay, the tops and or bottoms of the output signal will be cut off because they will be exceeding your maximum possible voltage. So you're going to turn this knob back and forth until you get the largest signal that you can without cutting off the tops or bottoms. All right? And then you're going to plot the what you see on a graph here. And then the last part of the lab is that you're going to change around the load resistor. So you're going to leave the rest of the circuit the same, you're just going to change out that load resistor. So when you first built the circuit, that load resistor was 5.1 kilo ohms. And at the last part of the lab, you're going to change it. You're going to start making it smaller and smaller. And what I think you'll see is that the signal will become distorted. Okay? So what's happening is that this load resistor is determining the amount of current that this circuit has to supply. So a fairly high resistance, like 5 kilo ohms, means that you don't have to supply very much current, right? And that's good because we said that the common emitter amplifier was a voltage amplifier. It does not create very much current. So as long as it doesn't have to supply very much current, it's happy. When you start putting smaller resistors there, then it has to supply more and more current. The smaller the resistor, the more current this thing has to create. And it's not good at creating a lot of current. So what happens is that when you force it to do that, it distorts your signal. So you're going to put in some smaller and smaller resistors, and the smallest one is going to be about 8 ohm. Any idea why we might choose 8 ohms?
Speakers.
Yeah, a lot of speakers are 8 ohms. So if you put an 8 ohm resistor there, you would see what the signal might look like if you tried to drive a speaker using this type of amplifier. All right. So that's what we're going to be doing in lab tonight. Any questions about that? Yeah.
So on the subject of speakers,
Clipping will ruin your speakers.
Right.
If we don't have a speaker in this circuit, is there anything that's going to get ruined if we have like clipping?
No. No, I mean, it's not going to hurt any of our components, but the idea of a common emitter amplifier is that you want to have a very nice reproduction of the signal. So generally, this is the first stage in an amplifier. So you want to take a small signal and increase the voltage while adding as little noise as possible, distorting the signal as little as possible. So we're looking at sort of the limits of this circuit and what it can do and what things will introduce noise and distortion to the circuit. Does that make sense? Kind of. Other questions? Okay. Then let me take attendance and have a break.